Call the meeting to order. And our first line item on the agenda is always the meeting minutes from February or last month. So the minutes are available in the members area on the website. So if anybody's had time to go through that and check them out, if there's any questions or concerns about them. No, seeing none. Okay, can I get a motion to have the minutes approved posted on the members area? And your name again? David. Okay, seconder. Oh, I see Dave Buckle in the back. Okay. All in favor, say aye. Aye. Opposed? None. Okay, great. Okay, next is the treasurer's report, which is going to be done by Yusuf Hussein. Jeff Whiten is not available tonight. Yusuf, in the last few months, we've been looking, Yusuf has been helping Jeff with the finances and treasurer's role. And it was, over the last couple of months, it's been figured out that we need, Jeff needs a little bit of help. So basically what we've done is Yusuf has come on board, and at the last council meeting, we created a position called finance director. And that person will be working with Jeff on a daily basis or monthly basis, whatever they need. Where Yusuf will be working mostly on a lot of the day-to-day stuff, freeing Jeff up to do the planning, the financial planning, all of the paperwork we have to do with the government and AGLC. So Yusuf is going to give us the presentation today on the numbers in the bank account. Plus, we're also he's going to give us a little information on the new processes for doing incoming expenditures. So Yusuf, if you can come up here now, and Frank, if you can bring up the treasurer's report. There we go. Thank you.
All right, so to start off with, he said I should at least introduce myself a little bit to anyone who doesn't know me. Ironically, I was a RASC member back in the 80s and early 90s, got kids, lost money, fell out of it, and didn't really do anything with RASC for a number of years. And then back when the pandemic hit, I read a few things and started saying, man, I could maybe do photographs more better than I did in 1995 because the technology's there now. And I was looking at some stuff, went, oh shit, this looks pretty good. Sorry if I use colorful words once in a while, just who I am. Technical term. And then I said, well, what the heck? I haven't done RASC for a long time. Let me sign up and start to come to the meetings again. And he was right. A couple months or about 4 months ago, I kind of said hello to Jeff and said, do you need any help? How does things work with the treasurer and that? And he listened to me talk, and we talked for a little bit, and he quickly went, damn it. From his point of view, he was like, damn it, yes, I want this guy. As he said, he does have a lot of work, so he was like, I don't want to offload as much work as I can to me. So he finally got this new position, and I'm kind of laughing tonight because Jeff says, I get this new position, and what does he do? He says, oh, I'm not going to be here tonight, so you can do this whole presentation tonight instead of me. So here we go. So I'm going to present tonight on 2 topics, and I'll start with just the financial report for February. And so for the February report, we have a starting balance like last month at $58,062, and we're ending at $54,585. And this is the casino account, I should start off by saying. And there are only a few expenses that we're mostly dealing with as usual, Plane Wave. It's a big project that we're doing, and some operations for BNLO. In the case of the general account, it's gone from $58,595.67 to $83,984. Credits were from membership dues and some rebate for the Jasper Dark Sky Festival. There was only one expense, and Jeff made a little mistake when he did our GST rebate and got double the amount. And so he had to repay back government half the rebate. So that way we don't get in trouble with the government. And then for the Bob Drew Telescope Fund, there's no change again. It's still sitting at $1,227. So as they mentioned, I'm going to be doing we've done a little update to the expenditure proposals. And so tonight I'm just going to give a little intro to the update. So first of all, do you have an idea? And then I finally thought to myself, did you know that anyone in this room can have an idea that they could submit for spending ideas? Not all of your ideas have to be massive. They don't have to be plane wave. They don't have to be BNLO. Don't have to be multi-year projects. So everyone in this room has this opportunity. So first of all, this is actually not a new policy that we've created. There was already an existing policy and form out there that was used for people to submit expenditure ideas. So what have we done in the last few months? Well, one is to actually create a formal policy, because it was really informal. We had a form, you could fill it in, but there really wasn't much instructions with it if you hadn't done it before. But on top of that, we did adopt a few changes to how we wanted to work. And so mostly what I'm going to focus on in the next little few minutes is just those changes and differences. So the first major thing we changed is, rather than just having, before it was kind of only done around budgeting time in October, now we want to have 2 intake periods. So we're going to have one intake period in the spring, which will be April. And of course, it's just before the April council meeting, and the fall intake will still occur just before the October meeting. So if you want to submit, you want to submit prior to those 2 council meetings. And so in case of this year, one is coming up only in a month and a half from now. So it's a great time to consider a submission. And so that's April 27th. And of course, the fall one will be, the council meeting is on October 26th. So what happens after you submit? And so once in those 2 intake periods, we'll basically bundle all the submissions up, take it to council, and at that point, council will review all the proposals and prioritize them, and then basically make a decision on each one. And the approval is basically based on how much funding we have, what priorities we have as an organization. And of course, the one other caveat, as some of you are aware, is if the request is over $1,500, final approval comes to the membership at the next membership meeting. One of the changes that we're making is having a little bit more understanding of what happens if you don't get approved. And so if the reason you're not getting approved is because there's not enough funding available, then you'll automatically be, your proposal will automatically added to the next intake period. And so for April, it would basically go into October, October would go to April. If your proposal is not approved for 2 intake periods, it'll automatically come back to you, and it'll give you a chance to look at it, confirm the funding that you're requesting is still correct, because that means a year will have gone by and maybe the numbers are not right. So we want you to verify and submit it again. That way we don't have our main goal there, which we used to have a problem before, things that would just hang around for years and not really get decisions made on them. Then for all other reasons, if you're not approved, you're actually going to you would expect a response from council after those 2 intake periods of explaining why and what they might recommend for you to attempt to do for the next intake period. What if your proposal is approved? Great. Your funds will be allocated for the budget. And the most important thing, you are responsible for the execution. Don't forget that. And so it doesn't mean that council is going to take care of it. You will have to take care of it. Now, of course, you can obviously work with a bunch of people, whichever project you're doing, but you become responsible for it. And then, of course, as you do your expenses for it, there's a separate policy out there already on the RASC site for how to submit your expenses when you're completed or as you work on your project. So how to get more information. So this was just a brief overview, and there's not a whole, there's still a few other changes in the policy, things about what happens if you go over budget and all this type of things. So if you want to get to the fine details, you can go to the members area on the RASC site, and there's a new section called policies, and the expenditure proposal policy is what you're looking for. So take a look at it, and then everybody who's maybe in the process of doing one or has done one before, I'll also make you know that the actual form has had 2 minor changes to it. And so for all of you that have done this before, throw that one away and please download a new version. And of course, also on the policies area is, of course, how to do your expense reimbursements. And that's all for a quick update tonight. And now we can get to the fun of the presentation.
So tonight for our guest speaker is Brianna Ball from the Department of Physics, U of A. Her topic is the stellar graveyard, exploring our galaxy with radio eyes. Brianna is a PhD student studying astrophysics at the University of Alberta. Her research focus on radio observation of galactic supernova remnant. She previously studied mathematics at the University of Saskatchewan and education at the University of British Columbia before coming to Edmonton to study astronomy. She is passionate about teaching and learning, promoting diversity in STEM fields, and making science more acceptable to everyone. So without further ado, I'll invite Brianna up to do her presentation. There's your laser pointer, button on the very top.
Okay.
Okay.
Thank you.
And as soon as Frank gets it up there, you can go ahead. You can hold that if you want. You can just stand right in front of it.
Okay, then I'll just stand here. Okay. Thank you for having me here. So today I'm going to be talking about our galaxy, the Milky Way, and specifically what we can learn about its supernova remnant population with radio observations. So I thought I'd start just by talking about radio astronomy generally. So just starting simply, when we talk about radio waves, we're talking about the lowest energy form of light. So this is going to be our light with a very small frequency and a long wavelength. So when we're talking about radio waves, we're typically talking about wavelengths of centimeters to meters. So very long. And when we look at our galaxy in different wavelengths, obviously we see very different things. And one of the advantages to looking in the radio is that we can see a lot deeper than we can see in some of the other wavelength bands. And this has to do with that long wavelength. Because of the long wavelength, it doesn't interact, radio waves don't interact with dust and gas as much as, say, optical light does. So we can probe a lot deeper into the galaxy without the light being absorbed or blocked by the gas and dust. Let's go to the next slide. So one of the other things that's kind of unique about radio observations is that they can be done from here on Earth. Radio and optical are the only two frequency bands that we're able to do this. And this has to do with the fact that the atmosphere filters out other wavelengths of light. Obviously, in many ways, this is a big advantage because you don't have to worry about getting your telescope into space. You can fix it if it needs fixing, but it's also a particular advantage in the radio because the thing about radio telescopes is that they have to be very large. And this is due to the fact that the resolution of your telescope depends on the wavelength of light you're looking at, and specifically the ratio of that wavelength to the sides of your telescope. So longer wavelength, you need a bigger telescope. So because of that, radio telescopes tend to be very large. So we can go to the next slide. So a few examples of some radio telescopes. The closest one to us is in BC, just south of Penticton. Maybe you've had a chance to see it. The Galt's 26-meter telescope, so it has a diameter of 26 meters, has been operational, I think, since the 60s. Of course, one thing we also have to consider when we're doing ground-based astronomy is that what we see in the northern and southern skies are very different. So it's good to have telescopes in both hemispheres. Most radio astronomy in the southern hemisphere is done in Australia. So we have telescopes like Parkes there to help us out. And then I also include here an image of the Arecibo telescope in Puerto Rico, even though it collapsed a few years ago, just because it, for a long time, was a very important radio telescope. And I think it gets at one of the challenges with radio astronomy. If you look at the design, it's actually built into a natural sinkhole in the ground. But there is a practical construction challenge, which is we can only build these things so big before they start to collapse under their own weight. So how do we get around the fact that there is a practical limit to how big we can build our radio telescopes? So you can go to the next slide. So that's where interferometry comes in. So this is where rather than just building bigger and bigger telescopes, we instead build many telescopes. We point them at the same point in the sky, and then we take the signals from those telescopes and we can combine them to form a single image. And when we do that, we get an image that is much better than either or any of the single dishes could make on their own. So with our interferometers, our resolution is no longer based on the size of our telescope, but rather on how far apart they are. So we call that the baseline in radio astronomy. And so your interferometer, the resolution is now set by the longest baseline, so the longest distance between your dishes. So that means you can have the dishes spread out up to kilometers apart, and you can achieve the resolution that a telescope would have if it had a dish size of, say, a kilometer. You still do have to fill in that space. You can't just take two telescopes, build them really far apart and call it a day, because we're concerned with our coverage, so how well we're actually capturing the light in that region. So we have to be strategic about how we place those telescopes to maximize our coverage while dealing with costs, of course, and other things. We also have to consider a bunch more complicated things, like we need to account for the fact that our light travels different amounts to get to our telescope. So we need to account for that when we're combining the signals. We have to deal with things like that. The atmosphere may be different above our telescopes because they're located so far apart. So it does get very complicated, but it's worth doing because interferometry is so powerful. So we can go to the next slide. So here are some examples of interferometers. Most modern radio astronomy involves interferometry in some way. Probably the most famous radio telescope is the VLA in New Mexico. It's American, so it gets to be in TV and movies sometimes. Close to us, we also have an interferometer at the site in BC. Similar idea. Both these dishes are actually on train tracks, so they can be moved into different orientations depending on what frequency you're looking at. At the Penticton site, we also have CHIME, which you may have heard of. CHIME has a very different design than other radio telescopes. It has these sort of parabolic receivers with the focus kind of along the center here. And CHIME was designed to look at a huge part of the sky at one time. It can actually survey the entire sky in one night. So that's why CHIME has been really good at catching fast radio bursts. So which are just what they sound like, fast bursts of radio emission. And because it's looking at such a huge part of the sky at one time, it's really good at catching those things. In the Southern Hemisphere, we have ALMA in Chile. ALMA is kind of, in some ways, the opposite of CHIME. It looks at a much smaller field of view, but it has a very high resolution. So you can see a lot of fine details. It also observes at a relatively high radio frequency, so you kind of see different things than you would at lower radio frequencies. We can go to the next slide. Oh, perfect. Okay, great. That brings me to the latest generation of radio telescopes, the big two being ASCAP and MEERKAT in Australia and South Africa. Mostly I'm going to be talking about ASCAP today because that's the telescope I mostly work with. But both of these telescopes just started their full operations in the past few years. So we're just really starting to see the results come in. They were both built as precursors to the SKA, or Square Kilometer Array. which is sort of the future of radio astronomy. So this is a huge international collaboration to build kind of the best radio telescopes we can build. It's actually two components. There's SK Low, which will be in Australia, and SK Mid, which will be in South Africa. So these are actually currently under construction. SK Low, as the name suggests, will look at very low frequencies, somewhere in the range of 50 to 350 megahertz, which is extremely low even for the radio. And the telescope design for SK Low is kind of unique. We have all of these sort of little metal things that look like Christmas trees. And these are actually the antennas. So the longer components at the bottom will look at the longer wavelengths of light, and then the ones at the top will look at the shorter wavelengths. These little metal Christmas tree branches are actually dipoles. So the antennas catch the signals and then they get digitized. But each of these little clusters will have, I think, 256 antennas, and there will be 512 of these clusters. So that many antennas total. But since they're essentially pretty simple components, we can build that many. They'll be spread out up to 74 kilometers. And so, and then these are actually, so these are just artistic creations because the telescopes aren't built yet. But when I was in Australia recently, I actually got to see one of the SKA low antennas that they had in a building there. So this is what they'll actually look like. And these are currently being assembled and put into place right now. And then in South Africa, we will have SK Mid, which it will be the mid to high frequency range. So these will be combined with Meerkat. In total, there'll be 197 dishes spread out over 150 kilometers. So radio astronomers are really looking forward to when these things start to collect data, which I think is scheduled to be sometime in the 2030s. So, you know, relatively soon. Okay, so now let's talk about astronomy. So most of my work is focused on our galaxy, the Milky Way. Obviously, we know it's a spiral galaxy with a nice central bar. From the side, it looks like a flat disk, though there's some warping at the edges there. We are located somewhere around here, I think 26,000 light years from the center. And so these are not actual pictures of our galaxy. They are just artist sketches because we can't get a picture of our galaxy. And that's because we're inside of it. And that's kind of the main problem we have trying to study our own galaxy, is that we can never get these sort of top-down views. We always have to look from within. So when we are studying our galaxy, studying the solar neighborhood, so the area around us is a lot easier. When we start trying to look across, especially across things like the galactic center, which is really dense with a lot of sources, we have trouble seeing through all that. So probably the biggest question mark is what's going on over here, because we can't see through all this stuff. And so this is where radio astronomy can be useful. We still have the issue of, like, if you have a long line of sight through the galaxy, there's going to be a lot of sources along that line of sight. But at least in the radio, we don't have to worry about things like gas and dust getting in our way. So we can see quite a bit deeper than we can see in, say, the optical. And then unfortunately for us, the Milky Way is best viewed from the southern hemisphere, though maybe fortunately for me, because I'm using ASCAP. But so everything I'm going to show you today is from the southern hemisphere, and that's where we can see things like the galactic center and the more dense, rich parts of the Milky Way. So as I mentioned, I primarily use ASCAP, and all of the ASCAP surveys are named after Australian animals. So I use two surveys called Emu and Possum. Technically, these are acronyms, but they're kind of forced acronyms, like many things in radio astronomy generally. But they are radio surveys that will eventually cover the entire southern sky. So they are ongoing. They're about halfway through. And they, as I mentioned, are being observed with ASCAP, which is an interferometer. It's made up of 36 12-meter dishes spread out over up to 6 kilometers. And ASCAP also has a very wide field of view, which makes it good for these kind of large-scale surveys because it can do them a lot faster by looking at a larger chunk of the sky at one time. So EMU is our more typical radio survey. It's at a low to medium radio frequency, around 943 megahertz. And then Possum is essentially the same region, but only looking at the light that's polarized. And so I'll talk a little bit more about polarization in a bit. So this is what part of our galaxy looks like in the radio. So you can see here, we have the galactic plane running through the center there. So you have these kind of denser regions with some sparser regions in between. The dense regions where we see a lot of really bright emission, that's where we're looking along like a spiral arm. So within the spiral arms, there's a lot more going on, a lot of stars, and a lot of other things that produce radio emission. So we see those kind of dense clusters and then kind of sparser regions in between. And it's in those dense clusters that we really have trouble figuring out what's going on there because everything is so overlapped and messy. So this part of the galaxy is kind of in this region here. So we're not looking right at the galactic center, but we still have a pretty long line of sight through the galaxy. So there's a lot going on here. If you look more towards the outskirts, it's less interesting. There's less going on there. So we decided to start with this region here. Okay, now let's talk about supernova remnants. So when a star explodes, everything that was in the star has to go somewhere. So it goes into a huge expanding cloud of gas and dust that we call supernova remnant. Because space is such a low density environment, these things can survive for a very long time. So we actually see them for tens of thousands of years after the star exploded, because it takes a long time before they actually merge and rejoin the interstellar medium. But they're a very important process because they are how all of the things that used to be in the star get put back into the galaxy. So all of the energy that was in the star, but also all of the heavy elements that were fused in the star. Oftentimes in the remnant, we can find what we call a compact object. This is where you have if a massive star explodes, the core will become a neutron star, a pulsar, or even a black hole. So if it's a neutron star or a pulsar, we can often find it within the remnant in the radio. But studying supernova remnants is important for many reasons. They play an important role in the galaxy. Not only do they recycle all those materials to make the next generation of stars, but all of that energy that's being injected into the galaxy will affect how the galaxy evolves. It can move things around, create regions of higher or lower density. And so understanding supernova remnants as a population is important for understanding our galaxy as a whole, if we want to understand kind of how it's evolving and changing. And so if we look at supernova remnants in the radio, they can look quite diverse. There are kind of three main types that we group them into. We have our classic shell type remnants. This is what most supernova remnants look like. So this is where you have most of your emission concentrated in sort of an outer shell feature. And then you'll notice there's sort of a hard edge, which is evidence of the supernova shock interacting with the interstellar medium. So when we see those sort of hard edges, that's a good sign that we might be looking at a supernova remnant, because we expect that to be produced through a shock. In our shell-type remnants, we also might see some secondary filaments running through the center. This happens if you have sort of asymmetries or weird things with the density in your environment. You can get a bunch of secondary filaments that form as well. But we're still looking for these sort of thin shell features and hard edges. The second type of remnants are what we call composite sources. So this is where you have the outer shell structure. So just like with the shell type, but then you also have this really bright nebula in the center. That bright nebula is what we call a pulsar wind nebula. And so it is produced when your supernova explosion creates a pulsar, which is just a neutron star that is rotating really rapidly with a really strong magnetic field. And that rapid rotation and strong magnetic field creates a pulsar wind, which is essentially just a bunch of fast-moving particles, which then interact to produce really bright radio emission. So if we see something like that, we know that there's a pulsar somewhere in there powering that nebula, which then exists inside the larger supernova remnant. And then the third type is we can also have a pulsar wind nebula just by itself. Sometimes if your explosion occurs in a really low density environment, the shell might be too faint so that we don't actually see it. So that's like what you would see here. This is actually the whole thing is a pulsar wind nebula. And then in some cases, the pulsar actually escapes the supernova remnant. So if the supernova explosion is asymmetric, sometimes the pulsar gets a little velocity when it's born. And so that velocity sends it flying off into space. And as it travels through space, it creates its nebula, but it sort of drags it behind it in kind of a tail feature. So if we see something like this, we call this a bow shock pulsar wind nebula, and that indicates that it is traveling at a very high speed as it escapes its supernova remnant. So these are relatively rare to find on their own, but we still do find them sometimes. Okay, the other main source of radio emission in our galaxy is what we call H2 regions. H2 is just what astrophysicists call ionized hydrogen. So essentially hydrogen that has the electron and proton separated. And this happens because if you have a very young, bright star, it produces UV photons, which are energetic enough to ionize the hydrogen. So those UV photons interact with the hydrogen gas, free up the electrons, and so then you get a nice plasma of ionized hydrogen surrounding your star, and that also produces bright radio emission. So these are our two main sources of radio emission, supernova remnants and H2 regions. And a lot of what my work focuses on is trying to tell the difference between the two, because they can look very similar. So the supernova remnant population of our galaxy is largely believed to be undersurveyed. We know that a supernova occurs in our galaxy about once every 40 years. What we don't know is exactly how long we should be able to see them in the radio for. And this is because that can really vary depending on the conditions you're looking at. So if you're looking at a higher low density environment, if the explosion occurred near to us or far away, all these things can affect how long we would see it for. Currently, we've discovered somewhere in the range of 300 to 400 supernova remnants in our galaxy. That range is just because there are some sources where we're maybe more or less certain than others. But what we do know is that there should be at least 1,000. That's something most people agree on, and possibly up to a few thousand. So we know there's a discrepancy there. We also know that we've identified a lot of sources as possible supernova remnants, but we haven't been able to definitively confirm them as supernova remnants. So there's over 400 other sources that have been proposed as candidates, but not confirmed. And so this plot is just showing how the number of supernova remnants in our galaxy that we know of has increased over the years. And these big spikes tend to correspond to new radio surveys, because that's primarily how we discover supernova remnants. And the reason for that is, one, supernova remnants are just very bright in the radio, so they're easy to see. Almost all supernova remnants are visible in the radio. And then the other part of this is what I mentioned before, that when we're observing within our own galaxy, we have to deal with the fact that there's a lot of gas and dust, which absorbs shorter wavelengths of light. So in the radio, we don't have to deal with that problem, though we still have to deal with the fact that there are other radio bright sources, most of which are H2 regions. Okay, so back to our galactic plane image. So how do we go about picking out what everything in this image is? Even if you have studied this for a long time, this is difficult to do. And so I will add some annotations to help us out. So the cyan circles here are the H2 regions. The red ones are known supernova remnants. The orange and white are candidates. And then there's some little green stars in there, which represent where the young pulsars are located. And we like to know where the young pulsars are because that tells us that a supernova occurred there recently. That's the only way you can get a pulsar. So that might be a good place to look for a supernova remnant. But so how did we go about deciphering all of this and figuring out what everything is? So to do that, we primarily rely on the fact that H2 regions and supernova remnants produce their radio emission using different mechanisms. So H2 regions primarily produce radio emission through a process called Bremsstrahlung emission, which is German for braking radiation. Essentially, when an electron moves past a positively charged nucleus, it's attracted to that nucleus, which curves its path. That curved path is an acceleration, which results in radio emission being produced. So this is primarily what you see when you have an ionized gas. For supernova remnants, they primarily produce radio emission through a process called synchrotron radiation. So this is where you have relativistic particles, so particles moving very, very fast, interacting with a magnetic field. So this all occurs in the supernova shock front, so that thin shell I mentioned. The shock accelerates the particles and compresses and enhances the magnetic field. And so what happens then is those really fast-moving particles start to spiral along those field lines. That curves in their path, similar to the previous example, is an acceleration, which results in the production of radio emission. So because these two sources produce their radio emission using different mechanisms, we can look for the signatures of these mechanisms to try to distinguish between the two types of sources. So the first thing we look at is just what it looks like. So as I mentioned, with supernova remnants, we're typically looking for those thin shells with hard edges that indicate a shock interacting with the interstellar medium. But then the next thing we can look at is whether or not the radio emission has a counterpart in the infrared. So what you see here is a composite image with the radio emission in red and then infrared emission in blue and green. And when you do this, the supernova remnants start to pop out because they only have the red emission, whereas the H2 regions have the blue and the green. This is because H2 regions should have a really strong infrared counterpart, whereas supernova remnants don't. So if we find a source that lacks an infrared counterpart, then that means it might be a supernova remnant. This is generally how candidates are proposed. So when we make our lists of candidates, it's typically done this way because you can do it relatively quickly just by looking. But it's typically on its own not enough to actually confirm those definitively as SNRs. So once we have our list of candidates, we can look at them a little more closely and try to get stronger evidence to confirm them. So one way we can do that is by looking at their spectrum. So this is just looking at how the brightness of the source changes as you look at different frequencies. So for H2 regions, we expect the brightness to be relatively constant as we increase the frequency, at least for the part of the spectrum we would typically be looking at. For supernova remnants, we expect them to get progressively fainter as we go to higher and higher frequencies. So if you observe your source at a bunch of different frequencies and look at how bright it is, you can create a spectrum, and then based on that spectrum, determine which of these sources it is. So when you do that, it looks something like this. So this is a supernova remnant spectrum. We can tell because it decreases very significantly as we increase the frequency. The problem with this is that you need multiple observations to be able to make a spectrum. You can't do it with just one data point. And the more data points you have, the more certain you can be. So this data isn't always available, but if it is, we can create this nice spectrum and prove it that way. We can also make spectral index maps. So this is showing how the spectral index changes for over the source. So this is a supernova remnant, and this is an H2 region. And so you can see supernova remnant has a nice steep spectrum throughout, whereas the H2 region is much flatter. So if we don't have all of that data available, another thing we can look at is polarization. So polarization just refers to how the light waves are oriented. An unpolarized source, it looks very random. So that's what you see on the left here. So you have this sort of more scramble where all of the light waves are kind of in a random order. Whereas polarized light, you expect it to be all oriented along the same plane. So if we find a source that's unpolarized, it's more likely to be an H2 region. And if we find a source to be polarized, then we know for certain it's a supernova remnant because we don't expect polarization from an H2 region. So this is now looking at the same part of the galactic plane, but just looking at the light that's polarized. When we do this, we have to be careful because there are instrumental effects that come into play. But if we can show polarization is real, then we can confirm a source as a supernova remnant. Here are some examples of supernova remnants that we were able to confirm as such using the polarization. So what you see on the left is the supernova remnant in the total power image, and then the right is the polarization. And so you'll notice often we don't see polarization from the whole source. A lot of times it's just from the brightest part of it. This is because light can become depolarized if it interacts with a magnetic field. Essentially, a magnetic field can sort of scramble up the polarization and make it not polarized anymore. And so what we found is that sources that are located at high latitudes, so either very far above or below the galactic plane, are more likely to be polarized because the galactic plane has a depolarizing effect. There's a lot of magnetic fields there that can interact with the light to depolarize it. With these surveys, we were able to, so we looked at a region which had 44 known supernova remnants and 46 previously identified candidates, and we found 43 new ones, as well as confirmed 14 candidates, mostly using polarization. So polarization, I think, is going to be an important tool for actually confirming the supernova remnant candidates, particularly at high latitudes, which is a big hurdle in these studies, trying to actually confirm the sources. Okay, so looking forward, we're mostly missing the old faint supernova remnants because these are very hard to pick out. It's hard to see faint sources, especially in those really dense regions, and it's also really hard to confirm them. If we could confirm all of our candidates, we'd actually be pretty close to resolving the discrepancy. But of course, we haven't been able to do that. So looking to the SKA, SKA low could be particularly useful for looking at these faint sources because, as I mentioned, supernova remnants have that steep spectrum, which means they get brighter as you go to lower and lower frequencies. So even the very faint sources will be brighter if you go to the lower frequencies. And then for SKA mid, for polarization, it's actually better to go in the other direction because depolarization is a frequency dependent effect. It gets worse at lower frequencies. So if you go to higher frequencies, you're more likely to see polarization from those sources located within the galactic plane. So that could be useful if we want to actually confirm some of those sources as well. But yeah, that is all I had for you today. So if you have any questions, I'd be happy to take them.
Okay, is there any question for Brianna? Oh, go to the back first.
Thank you for the talk. How large are the SKA low antennas? They look like Christmas trees, but how tall are they actually supposed to be?
They're about 6 feet tall.
Oh, Christmas tree.
Yeah.
Okay.
Won't fit in your backyard. Next question. Okay. Ken over here.
Thanks for the talk. You mentioned fairly early that when a supernova blows off, it distributes a lot of material around and pushes things around. Is there any evidence that you've seen or that anybody has seen that the presence of a supernova will trigger other supernovas so that you would get more than a statistical likelihood of a supernova if you have a denser star area?
So it depends. I mean, so often how supernova occur is if you have, say, two smaller stars in a binary, one accretes off the other. So one takes material from the other one, and that's why it explodes. But when that happens, I don't think it triggers a supernova. It more just blows everything apart. Because for a supernova to occur, you need sort of specific conditions. You need the star to actually start to collapse on itself and then rebound back out, right? So more likely, I think you would have the system just becomes unbound and goes off that way. But we do tend to see like they occur more often in the denser parts of the galaxy because that's where all the stars are.
You've got time for two more questions. Wait a minute.
Thanks for the interesting talk. Thinking about the distribution of supernova remnants, would it be true to say that in OB associations or around those where you're getting lots of high mass stars that you would get clustering of the supernova remnants?
Yes, and that's part of the problem is that so the high mass stars are going to be associated with both H2 regions and supernova remnants, right? Because both of them are associated with young stellar populations. So it's all within these really dense regions. So that's probably where we're missing most of them, is where you have all of these young massive stars. And so you have the dense regions of radio emission. And so that's one thing kind of we want to look at is are we seeing the expected distribution of supernova remnants line up with the H2 region distribution? Because they should match quite well since they're associated with the same kinds of stars.
Okay, online.
I have a question online, if you can hear me. I've photographed it a few times when I've been in Australia. Is there any now further study on what the identity of the huge Gum Nebula is? Gum 20, I think it is, in Colin Gum's catalogs. That big 30-degree wide nebula in Vela and Puppis. I read that it's a supernova remnant. Others say, oh, no, it's just an H2 region. On your work, and is there any further work on what it is?
Well, so with ASCAP, the Vela supernova remnant is currently only partially covered. So we're actually just currently getting that data coming in. So hopefully soon we'll have some more information. Currently, I don't have anything yet, but we are the surveys are ongoing. So we are getting new information coming in. We have it about half of Vela, I think, currently.
Thank you.
Anything else online, Frank?
I have one.
Okay, go ahead.
You talk about these meter long or longer radio waves, and you talked about how some of the atoms sort of react with the radio waves and give you some detail. But I'm totally confused as when you get these radio waves, these great big long radio waves, how do you convert them? What's the technology behind making them into those crisp pictures that you're showing?
It's very complicated. It involves a lot of math. So the telescopes each, they have the dish focuses the waves on the receiver, but then that signal gets digitized, and then they all have to be combined and correlated, and then there's some mathematical processes that happen to actually produce the images. So it's kind of complicated and technical. But yes, there is a process that has to go through before you actually get the images.
Okay, thank you.
It just confused me more.
I still find it confusing, so I don't know if I can help.
Start studying for your PhD and you might be able to figure it out. Okay, thank you, Brianna. On behalf of the Royal Astronomical Society, we're going to give you an observer's handbook. I don't know if you have one, but if you don't, you do now.
Thank you.
Okay, thank you, everyone. Okay, Murray's going to be giving us a quick update on the observers group.
Thanks, Clayton. Thanks, everybody. Alistair Ling and I are sort of hosting or leading the observers group this year. And let me see. There we go. It's for all stargazers, no matter how inexperienced or experienced you are. We try to get together in city, and I've talked with you about this before. Sorry, better? Thank you. We try to get together in city, a short notice, and quick cancellations if need be, so we can do some basic work. And then on new moon, hoping to get out to some darker skies. Notices will come out on the Astro list and Facebook. And it could be any day of the week. The dark sky trips take longer, and hopefully a Saturday or Sunday, a Friday, Saturday, if possible. Oh, we wrote just last night. It's a very poor image. I think that's why I'm a visual observer. I took that. You can see Arcturus, though, out there. We had about 7 people and had a pretty good time between cloud banks. This is kind of getting past ourselves. I think the conjunction was actually a day or two ago. As we set up about 8 o'clock last night, Alistair and I were able to see Venus just between trees. It was really low, about 7 degrees up. And through my binoculars, I didn't see Saturn. It was too low. So looking for the blaze star, the Corona Borealis. It's getting easier to see in terms of Corona Borealis constellation is coming up earlier, around midnight now. And if you count the 7 stars, I count 1, 2, 3, 4, 5, 6, or just 3 from the brightest star in Corona Borealis. So this 6th star, 1, 2, 3, 4, 5, 6. In here, there's about a 10th magnitude star. About 80 years, it will blaze up to something that we'll be able to see naked eye. We've been looking at this for a few years now. Last summer, I went out every night looking for it. Then I realized it could be anything plus or minus 8 years or so. So I stopped. But it's still nice to look up. Do you see a star there or not? Coming soon, as Clayton mentioned. Spring, at least astronomical spring, March 20th. And with coming spring, coming summer, we now get about 7.5 hours or so of astronomical darkness. The sun is lower than 18 degrees below the horizon. But by May 11th, we're down to 0 astronomical darkness for the summer until early August. So get your observing in as you can. Now, in the Stardust, I put out a quick survey. Our last Zoom meeting, there was quite a bit of interest in what people use. Binoculars, telescopes, what people have, what's a good thing to buy first. And so I thought I put out a quick survey, and anybody's welcome to please complete it. It's anonymous. There's a barcode, or it's in the Stardust or on Astro list. The next observers Zoom meeting, Monday, March 24th, at 7 o'clock. Everybody's welcome to attend. And we're planning a 5-person panel to talk about their equipment, what their favorite type of telescope is, their favorite binoculars. And the results of the survey will be presented as well. So that's Tuesday. Oh, I said Monday. Tuesday, March 24th at 7 p.m. Thank you. Thanks, Dave.
Okay, one last thing before our break is our trivia, and I made it fairly simple this month because a few brain cells weren't functioning this week. 23 questions today, fairly simple ones. Number 1, how many moons does Mars have? Okay. Number 2, and also name them. What is the largest moon in our solar system? And name it. And what type of star is our sun classified as? So those will be near the end of the meeting. And we will now take our 10-minute break. And we'll get back with some announcements, presentation, book of the month, Astro Imaging Corner, trivia answered, and the final announcements. Okay, 10 minutes. Okay, everyone, if we can get you back to your seat, that would be much appreciated. We can get on with the evening. We've got a couple more presentations that are going to be done in right after the break here. So, okay. First item, we're going to be always talking about outreach opportunities that are available. If you are a volunteer that has registered with the logistics program with Dave Muscle, then we want you to check the calendar schedule on a regular basis and see if there's anything there that you might be interested in. The scope loaner coordinator. Looks like we have found our volunteer who stepped up to that. Later this week, we'll be announcing that Trevor Robert will be our new scope coordinator. Hopefully, we can get the program back up and running sooner rather than later. We want to do an audit and inventory of all the scopes and eyepieces that we have available. We're still looking for a VP, but for our executive committee is going to be working on that over the next month to find a candidate to fill into that position. And we have 2 presentations, short ones. Jay Lavender will be doing a presentation on the all-sky camera that we have out at BNLO. And then Alistair will give us a quick rundown on the fundraiser, the interloping comet that's coming through our solar system right now. So, Jay?
Hello, everyone. About a year ago, Kent Martins and I approached the BNLO committee and pitched the idea of installing an all-sky camera out at the BNLO observatory. And yada, 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 a few months go by and the Black Nugget Lake BNLO committee presented to an expenditure proposal to council, and council approved the project. And so Kent and I went and built the camera, and we deployed it just about a month ago now out at the compound. And I thought I would just show everyone some of the features of that camera and then let you know how you can access it. So without further ado, buckle up. The all-sky camera, by the way, software is written by a fellow, Thomas Jaquin. He wrote it about 10 years ago. It's primarily for a Raspberry Pi computer, and it's definitely a pretty decent piece of software, and he's made it public domain, so very worthy of Thomas's efforts, or mentioning his efforts. If you go to the all-sky camera during the day, it's off. And so what we do during the daytime hours is we just display the NOAA's auroral forecast, and we have a little blurb up top there saying, "Hey, come back in 10 hours to 6 minutes for a live view of the night sky." And you can see at the top right-hand corner a bit of a 3-day forecast as far as for aurora in your area. So the all-sky camera is aware of your lat long and will predict based on your position there. The timing is built around civil twilight. So once civil twilight hits, the camera will activate and it'll start taking a picture of the night sky. And that is one of the first pictures that we took of the BNLO night sky. And I believe that's Bortle 2-3 sky. And you can see why we wanted to put the camera out there. You can see the large antenna for internet access now out at the compound. You can see Kent added a thermopile onto the camera. And actually, if you look in the bottom left-hand corner, I'm scared to press the button here, but the bottom left-hand corner is that thermopile. And of course, it measures the IR radiation around it, I guess, in its field of view. And it tells us what the local or the current ambient temperature is, as well as what the sky temperature is. And as you can see, it's a nice warm -48 the sky temperature on that night. So the all-sky camera will update every minute. It takes a picture of the sky. And I mean, its primary purpose, I think, really is just to let you know what the conditions are out at BNLO. So if you're considering going out to observe out there, that gives you a pretty up-to-date picture of what's happening out there. So I wanted to just, again, I'm going to show some of the features here of what it does. And so as you could see on this picture on the left-hand side is that menu that has the 6 different icons on it. And I'll go through the top 4 for you just quickly. So, but I'm going to start with the star trail. So star trails is generated at the end of the night. So actually in the morning. So once again civil twilight ends, it will start generating the star trails, kilogram, and time lapse. And so okay, I'm lying. Sorry, we're going to go to sky overlay to start with. Sorry. So one of the features is that zigzag up top, which is the sky overlay. And if you're looking at that current picture and you click that that little icon, it will actually overlay what you're seeing in the picture with the constellations, with the stars, that sort of thing. Okay. If you look up here while you're actually looking at that image, you see this little question mark in a box there. If you click on that, it actually pops up this window, and these are the other things that you can press your keyboard shortcuts, and it will show things like the ecliptic line, alt as grid lines, that sort of thing. So something that you can play with while looking at the current all sky picture. Star trail. So this is the star trail. Sorry. So again, generated once the evening of captures completes. And so when you click that, you will get an archive. We'll keep about a month's worth of star trail pictures up there, and they're sorted descending. So the most current one is the first one. And if you look at that, that's one of the pictures that came out of there. I think that's beautiful. It's kind of neat. It's a beautiful sky out there. And so it collected that and built that. And here's another example of where we've actually had some aurora occurring while the star trails or throughout the night. So it gets captured in the star trails. You can see in some cases meteorites or meteors, sorry. Thanks, Murray. Don't tell Murray. And some aircraft also that have flown through the image, been captured in the image there. A kilogram, the all-sky camera takes the middle vertical line out of every frame that it takes throughout the night and assembles it into one single image. And again, if you click on kilograms, you get the archive, again, sorted descending, and then you'll see something like that. And so again, it's that middle line for every frame throughout the entire night. And so it gives you an idea that here you can see between 1900 and 100, it was cloudy. And then from then on, it cleared off. And again, you can actually see it's great for showing any meteors that may have crossed the sky throughout the night. And that's a picture, obviously, of one that we had a cloudy night. And then there's one of actually a fairly clear night throughout. That third icon, or I guess it's the fourth one now, is the time lapse. So again, at the end of the recording session in the mornings, the all-sky camera will take each frame and will assemble a time lapse. Usually takes it about 30 to 40 minutes to do so. And when it does, it will create a time lapse of the night. And Frank, if I could get you to start that. This is the picture of the night. And you can see obviously all the constellations. You can actually make out the Milky Way a little bit there. This is usually it's about a minute. Of course, the closer to summer we get, the shorter it becomes. We had the thermopile showing it takes a measurement every 30 minutes, but we have it constantly displayed now. It's blinking there, but anyway, I think it really demonstrates quite nicely how beautiful sky you get really out at BNO. And every once in a while, you'll see, again, you'll see meteors streaking across the sky. I have one of these all-sky cameras at home, and I'm alarmed at how often I see the police helicopter flying over my neighborhood. And yeah, so that's it for the time lapse, full screen. So any picture you're looking at, obviously you can click on that, see full screen, and the image, the information one, if you click that eye, this guy here, it just pops up this little card and has the information about where the all-sky camera is located. Where can you see it? Well, we've had our WordPress guru, Luca Vanzella, put a plugin on our website, on the main page of our website. So you can see it here, and it will actually display the current picture that the all-sky camera is displayed. So you can just go to edmontonrac.com and scroll down on the left side. Or you can go to the bottom menu on our main screen here, and there's the Black Nugget Lake. If you click on that, you can go there. You can also see the all-sky camera. Or if you would like to just go directly from any computer anywhere, of course, that has internet access, you can just go to edmontonrac.com/allsky and see the current picture, or again, the auroral forecast. So really that's it. Take a look at it. I find every morning with my coffee, I take a quick look and see what happened throughout the night if I wasn't there. And it's usually pretty interesting to see. If you're interested yourself in having your own all-sky camera, they're pretty easy to build. Again, the software is free. And but if you are interested in doing that, come see me and let's talk. That's it.
Thank you, Jake. Yeah, just go and check that at edmontonrat.com/allsky and you can see what's going on. Okay, next up we have Alistair Ling, who's going to give us an update on the Sungrazer firing through our solar system.
Great. Thank you. Well, some of your news feeds might already be trumpeting once-in-a-lifetime event coming up with this Sungrazer comet coming in. And well, I'll tell you a little bit about what to expect from here in Edmonton. Because, of course, you might be getting news reports from Los Angeles, New York, Helsinki, or Adelaide, who knows. So what is the Sungrazer comet? Basically, it's this is a particular family of comets that broke up about 1,000 years ago and has been dumping smaller comets in towards the sun that just graze the solar, outer solar atmosphere and produce sometimes these amazing comets. They're rare enough that the last nice one was 1966. You get about dozens of these things that are sort of too faint to be seen except on NASA SOHO images. So the hope, of course, is it's going to be like this or even better. And so where are we? So the sort of forecast is that it's coming along nicely. This is now a week or so out of date, but peak magnitude brighter than Venus, which sounds really bright, but that's a large-ish amount of sky crunched into a dot. So it'll be probably tougher than Venus, but at any rate, the comet comes into 160,000 kilometers from the photosphere of the sun. So it gets cooked. Will it survive? And of course, no one actually knows. So it's worth actually reading this. We all know comets are difficult to predict, but they're subject to intense heating, thermal stress, tidal forces, which lead to fragmentation. So it's not possible to predict whether or not this will survive perihelion passing the sun. There's a reasonable level of confidence that can be obtained by considering comets, the size, and how it's behaving at the moment. But as we all know, those expectations are tough to line up. So where are we so far? So this was updated just a little while ago, just a couple of days ago. The blue ones here are Ikeya from 1966. The green one in here is one of the Atlas comets that came by that dissolved on the way out and became a headless comet after perihelion. And the current one, MAPS, is coming in here. So it's starting to look like it won't be quite as amazing as Ikeya. So you might not want to spring for the airline ticket to the Southern Hemisphere, where the best show is going to be. Okay, so these are animations from Nicolas Lefaudeux, and these are just to give sort of street credit for the upcoming animation that I'll be showing you. So Hale Bopp as we all know. We see it from the side here. There's Orion coming through. Neowise from a couple of years ago had a nice tail, and it's a little tough to see the little gas tail coming off. But the idea here is that the upcoming simulation has some credit for you. So McNaught was the wonderful comet from 2006. And again, we're seeing here the orbit mostly from the side. We will not be seeing the Ikeya orbit from the side. So the tail tends to be that long, narrow one rather than this broad, sweeping arc there. But it's if his simulations can do really well with the comets that we've seen, the upcoming one ought to be good. So this is his simulation of Ikeya in 1966. So this is as viewed from the Earth, north up. You can see the Southern Cross down here, Leo up here. But the comet comes in, does a hairpin turn around the sun, and we're seeing the orbit from the edge on. So we only really get to see a sharp, narrow tail. And notice how, as it swings around the sun, we do not get any big spray of stuff. So that'll be a warning. The inbound will be pretty tough as it does that. The other thing that happens is that all of the dust that's in that orbit will, of course, vaporize as it gets close to the sun. So it actually disappears for a little while it's going around the sun. So this is probably what we're going to get for our one. There's the Hyades there. Orion will be coming in, so it's going to be an evening comet for us. I'll let this one loop yet again. Notice how the tail will sort of burn out, disappear, and reappear. So for that 2 days around perihelion, there will be no tail at all. And then if it doesn't survive, we'll get a bit of a tail as it breaks up coming around. So what's the view in Edmonton? So the evening view, there's the sun down here, the blue line's the horizon. This is the angle of the orbit. So essentially the tail as it comes in. This is the 30th of March. We probably won't see anything until then. It's about 10th magnitude now. But so the tail will be in this kind of angle during the evening for us. So as you can see, this is only a couple of degrees below the horizon. The sky will be bright. We will probably not see any evening tail on the comet at all from our latitudes. So it's like, what about if we look at it in the morning? And it's, nope. The geometry is such that the tail will be pointing below the horizon from our latitudes. So it doesn't matter if you try to see it in the morning. So the time to see it will be the 2 days before perihelion. Perihelion is April 4th. And it'll be a daytime. So hopefully we'll get to actually see it in the daytime. So find yourself a really nice building, block the sun, and then that way the sun will continue being blocked while you're looking for this little thing, and it'll be just a fuzzy dot, hopefully visible in binoculars and maybe even to the unaided eye, but be very, very careful. Put yourself in the shadow of the building first before looking up at the sun, towards the sun. Don't just sort of stick your hand up and block the sun. It's a very quick way of, partially blinding your eyes. So make sure you stand in the shadow of the building, and then you'll be safe to look up. On April 4th, do not try and look for this thing because it will be just simply way, way, way too close to the sun. So don't do it. And some of you are already going to be thinking, I have a hydrogen alpha filter. I can look at the sun during the day and doing it safely. Well, here's Mercury, 4,800 kilometer diameter, comet diameter, because there's no tail, remember, all of that stuff has been fried and gone, 4 kilometers, so 1,000 times smaller than this. Good luck. I can't say conclusively you will not see it in your H alpha images, but probably not. But who knows? Maybe in the time lapse you'll see a tiny little grain moving, but I doubt it. But hey, give it a try. So back to the day after. On April 5th, again, it'll be popping out to the left of the sun, so you can put the sun again behind a building edge, stand in the shadow, and then you can look up. So 2 p.m., just after noon, it's pretty much due south and high in the sky where the sky is transparent. Then we quickly shift over to evening view. And with the sun a few degrees below the horizon as the sky's starting to get darker. Now here we are on the 5th of April. The comet head will be below the horizon shortly after sunset, but the tail will be pointing out towards Orion. So you'll need a good southwestern horizon. And good luck. We'll see. And then here is what happens if it is an Ikea-Seiki type comet. We'll get the nice evening angle decently, and it might just keep on lasting and lasting until it gets all the way to Orion. But as you all know, Orion's setting, and it's still 1 month from today. So the background sky is going to be getting bright. And so, but get out there, look, use binoculars. If you are thinking, where's a better place on Earth to see this thing, south of the equator, and that will be the same for basically for all of the sun grazing ones, because that's its orbit. All of the sun grazers use the same orbit. So they're best seen from the southern hemisphere when the angle's really good. So fingers crossed, everyone. And probably don't wait for the announcement of, oh, last night it was really good, or yesterday evening was really good, because there's a decent chance it's going to fade quickly. And so get out there and give it a try. Thanks.
Thanks, Alfred. Okay. Next up is Book of the Month with Mark and Alfred.
Good evening. Greetings from the Lamplighter Library, from co-librarians Rosemary Ball and myself. Libraries open before and after the meetings to lend out books. And this month we have a continuation of putting books on the ledge over there that are surplus and duplicate books. And if you see a book you like, if you could leave a little donation in the donation box, that would be fantastic. As far as this month's book of the month, Gemini, Stepping Stones to the Moon, The Untold Story. Got some good news and some bad news. The good news is we have a nice review from Jeff Robertson, who just read the book. So this is what Jeff says. Between the one-man Mercury, NASA's first program to send a human to space, and the three-man Apollo, which took humans to the surface of the moon and back, there was Gemini, the two-seat spacecraft that in 10-man flights demonstrated the techniques and procedures needed to fulfill President Kennedy's 1961 challenge to land a man on the moon and return him to Earth by the end of the 1960s. I am of a certain age that the first book I ever read about Project Gemini came from my school's library in 1964. before the first crew had flown a single orbit. I followed the 10 crewed flights between 1965 and 66 religiously, getting up early in the morning to watch launches, following the mission on the news, and then waiting for the photo story in Life magazine to arrive in our mailbox after splashdown. Jeffrey Kruger, who co-wrote Lost Moon with Jim Lovell about the Apollo 13 mission, and who was the inspiration for Ron Howard's 1995 film, published a new book in 2025, titled Gemini Stepping Stone of the Moon. So this book. In its 271 pages, beginning with a prologue describing the near disastrous EVA during the Gemini 9 mission, Kruger recounts the early days of the space program and the politics that drove it, both in the US but also in the Soviet Union. It gets into the personalities of the day and the engineering and designs that were considered for the Gemini spacecraft. It delves extensively into a feature that I first saw in that book from the school library back in 1964, the Rogallo wing, a parasail that would deploy from the spacecraft instead of a parachute, allowing Gemini to glide to a landing on a dry landing on skids extending from the base of the craft. It was found to be too complicated, and parachutes were used for an ocean landing. Recounting the actual missions of each of the 10 manned flights does not begin until more than halfway through the book. It covers each mission fairly well, noting the highlights and some of the lesser known incidents of the missions. The chapters on Gemini 6/7 and Gemini 8 were very interesting to me. Although I did note something Kluger's editor missed. After Gemini 8 made an emergency landing south of Japan, it mentioned when the recovery ship reached the spacecraft and secured it, the crew opened their hatches and breathed in the cool Atlantic air. Oops. The epilogue begins with the Apollo 1 fire and ends with the moon landing. I've read many books about the space program as well as astronaut biographies. There were some things in this book that I had not run across before, but not a lot. Still, it's an enjoyable, quick read. For someone not familiar with the Gemini program and or the first decade of the space age, I would highly recommend it. So thank you very much, Jeff, for the review. So that was the good news. The bad news is that you're going to have to wait a month to get the book because it's already been taken out. This doesn't happen very often, I promise. So next month's meeting. Okay, that's about it. Rosemary, are we close to having the catalog available online or the library?
It's up there now.
Oh, it is up there now. Great. Okay, so and how can we access it?
There'll be a library page on the web, and it'll have the link that you put into your browser.
Okay, perfect. Great. So that's about it. Thank you very much.
Thank you, Mark. Okay. Next, we have Astro Imaging Corner, hosted by Owen, who is in front. He made it out of Mexico.
Thanks very much. Okay. I too was a Gemini kid and followed it religiously, loved the photographs, and I'm looking forward to reading the book. I might have to go to Audrey's or something. Yeah, I'd like to welcome you to Astro Imaging Corner number 154. So let's get going. Our first image is from Hans, who is our Bryce Hartwell Astro Imager of the Year for 2025. And he says that I've got 3 images from him, and they were all taken from Bortle 7/8 skies in Sherwood Park with a ZWO ASI 2600 MC Pro camera. The telescope was a Teleview NP127IS refractor with a 0.8x reducer for a focal length of 528 millimeters at f4.2. Image acquisitions were controlled by NINA, and images were processed in PixInsight. So the first image is of NGC 2174, aka the Monkey Head Nebula. He says for this SHO image, I shot with a 4nm dual narrowband filters for a total of 7.5 hours. So this is a narrowband image that he took. And he says he thought it would be nice to also see it in natural light, as he calls it. And this image then is only 2.5 hours in RGB, but since the nebula is quite bright, it shows some nice detail already. So those are really great photos, and I really like showing the difference between narrowband imaging and so-called natural light imaging when the light is in red, green, and blue. This is Hans's image of M31, the Andromeda Galaxy. He says it's a classic, of course. He says, here I'm combining data since 2023 for a total of about 12 hours, combined with an additional 6 hours of narrowband HA03 images to bring out the numerous emission nebula in that galaxy. So that's a tremendous picture. Hans, love it. I never get tired of seeing M31. So this is an image contributed by Craig Sherris, the Cocoon Nebula. He says, I took the RGB for this image last fall during the Northern Prairie Star Party and just recently processed it. So the date of this image is September 15th and 16th, 18th, 19th, and 20th, 2025. So the exposure is 138 5-minute subs in H alpha for 11 hours and 30 minutes. And then 269 3-minute exposures in RGB for a total of 13 hours and 27 minutes. So the total was 24 hours and 57 minutes. The telescope was a Stellarvue SVX 130T-R. The mount was a Software Bisque Paramount MYT. He says the Cocoon Nebula, cataloged as IC 5146, hangs in the northern constellation Cygnus as a compact cradle of starbirth wrapped in a sheath of dust and gas. It spans roughly 15 light years across, with angular measurements of about 12 arc minutes, translating to this true diameter, and lies on the order of 3,000 to 4,000 light years from Earth, placing it comfortably within our Milky Way's spiral arms. Through long exposure imaging, the nebula appears as a glowing red-pink sphere embedded at the end of a dark lane of dust. And that dark lane is cataloged as Bernard 168, creating the impression of a luminous cocoon trailing a smoky celestial tail across the sky. So very well described, Craig. And I love the wildness of this image. And I can't help but think that if this had been visible from Earth in the Middle Ages, armies would have just stopped and gone home. Okay, so what I did on my winter vacation in Bucerias, Mexico. Bucerias is a little town about 20 kilometers north of Puerto Vallarta. It's on the east side of the Bay of Banderas. Its latitude is 20 degrees north and has Bortle 5 skies. My wife and I have been staying in a condo by the bay the last few years, so it does offer imaging opportunities. So here are some images from February of this year. So I call this the Cheshire Moon, with apologies to the cat. The lighting from underneath the moon is reflective, if you pardon the pun of the southerly latitude. It was taken with a ZWO ASI 585 camera, a UV IR cut filter, and a 90 millimeter triplet refractor. This is 440 100 millisecond subs stacked with Auto Stacker 3 and lightly processed using Registax. It's a bit blurry on the big screen, but it's a little bit better resolved if you see it on Facebook. Anyway. Right. So Omega Centauri. So I've been going down to Bucerias for about 4 years and never had the opportunity really to photograph. And I've kind of like been Ahab pursuing the white whale. I finally, because it rises late for these 71-year-old eyes anyways. And, but I did bite the bullet and stay up till about 3:00 in the morning one night, trying to capture Omega Centauri. So it's astonishing. It's what I would call the King Kong of globular clusters. Like in our northern skies, we celebrate M13, the Hercules cluster, which has 300,000 to 500,000 stars. We think that's a big deal. Omega Centauri, 17,000 light years away in Centaurus, it contains 10 million stars. 10 million. So, but is it a globular cluster? When I posted this image on the RASC National Facebook page, Peter Jedicke of the London Center commented, Omega Centauri is regarded as a dwarf spherical galaxy nowadays, not a globular cluster. So there you have it. This was imaged February 20th, again using the 90 millimeter triplet, this time at prime focus, and a ZWO ASI 2600 MC camera. This is the result of 61-minute exposures combined using Deep Sky Stacker and processed using star tools. So I was very happy to see our presentation talking about supernova remnants tonight. And this is a snippet of the Vela supernova remnant, which is the remains of a star only 900 light years from Earth that exploded about 11,000 years ago. And I say snippet because the object as a whole covers 50 square degrees of the sky. And the field of view of this image is only about 4 square degrees. So yes, it's a snippet. There was some guesswork and a bit of a gamble involved in getting this shot because this northern boy was completely unfamiliar with the southern skies object. And, I was in Bucerias for a good time, not a long time. In other words, there wasn't much time for experimenting. And it was also cloudy for the first half of my stay there. So I did what I often do. I go to Astrobin, and the open star cluster NGC 2659 seemed to be present in lots of the grand stitched together images of this 50-degree space on Astrobin. So I decided to go to NGC 2659, take a 5-minute HA exposure, and see what turned up. So when I did that, there was a promising, faint, sort of smoky wisp above it, and that was good enough for me to commit. And in this picture, NGC 2659 is the almond-shaped cluster in the low center. This image is the result of 9 hours and 45 minutes of 5-minute exposures using the hydrogen alpha and oxygen 3 filters in my venerable QSI 683 camera. So in the processing, this hydrogen is mapped to red and oxygen was mapped to green and blue. And it was imaged from February 16th to 19th in Bucerias, again using the refractor and a 0.8 focal reducer. Subs were stacked with AstroPixel processor and processed using star tools. So, 3 clusters and a planetary. So this wide field image in the constellation Puppis shows the open cluster M46 at the left, with the little Cheerio of a planetary nebula NGC 2438 superimposed on it. To the right, the open cluster M47, and above it, the open cluster NGC 2423. M46 contains 500 stars and is 5,000 light years away and 29 light years in diameter. M47 also contains about 500 stars, but is only 1,600 light years away and is 12 light years in diameter. And NGC 2423 contains 50 to 100 stars, is 2,500 light years away, and is 9 light years in diameter. And I imaged this on February 14th using the 90 millimeter triplet with an 8.8 focal reducer and the 2600 MC camera. This consists of 140 60-second exposures for a total of 2 hours and 20 minutes. And they were combined using Deep Sky Stacker and then processed using Star Tools. Now, when I posted this on my own Facebook page, Ellen Dyer helpfully commented that another planetary, Minkowski 1-18, also appears in this photograph. And so I looked for it and found it. And I don't know if I can use this thing. And there it is. Oh, sorry. Where are you? Okay. But this one. Oh, okay. There it is right there. And it was found, it was only discovered in 1946 by the astronomer Rudolf Minkowski. And as you can see, it's small, faint, and reddish. And yeah, it just happened to get captured in the photo. So that was kind of cool. Here's another image from my time in Bousservius. This is a wider field view featuring objects in Orion. Orion is high in the sky in Bousservius, which does facilitate imaging. So as you can see, towards the top right corner is the blue reflection nebula M78. And the red semicircle at the bottom left corner is a small part of an emission nebula called Barnard's Loop. And that's a huge emission nebula. The image also shows obscuring clouds of gas and dark nebulae, not to mention stars, lots of stars. M78 is a stellar nursery that is 1,200 to 600 light years away, and it's about 4 light years in diameter. And reflection nebulae are blue because light is scattered by dust within them, much as how our atmosphere is blue. And by contrast, Barnard's Loop, which is 1,400 light years away, it shows up as red because it's an emission nebula, and the hydrogen atoms in the nebula are actually emitting light, and hydrogen emits in the red part of the visible spectrum. And as I say, it's large. It's a huge ribbon of red spanning 10 degrees, and it may be the remnant of a supernova. So this was imaged February 21st, 94 2-minute subs, using the refractor at prime focus with a 2600 MC camera for a total exposure of 3 hours and 8 minutes. Subs were stacked using Deep Sky Stacker and processed using Star Tools. So that's our presentation for this March edition. I'm looking forward to getting lots more images for April, and thank you very much.
Thanks, Tom. Get to the trivia answers, which should be, okay, how many moons does Mars have? 2, Phobos and Dima. The largest moon in our solar system is Ganymede, which is a moon of Jupiter. And our sun is classified as a yellow dwarf or G-type main sequence star, about halfway through its life cycle. Okay, go back there. We'll get to final announcement. Here's our cartoon of the month. Along with antimatter and dark matter, we've recently discovered the existence of doesn't matter, which appears to have no effect on the universe whatsoever. That was sent in by Hans Johns, and I think it's not a bad-looking cartoon. Okay, next monthly meeting is on Monday, April 13th, 7:30 Mountain Daylight Time. And I also mentioned here, watch for Artemis 2 launch party information from Telus World of Science. And Frank let me know tonight that they're aiming for April 1st as a launch date, April Fool's Day. So don't be surprised if it doesn't go. Okay. So if that is the date, and we got to confirm, we will be having a launch party, and RASC will be setting up a few tables in the lobby to talk about space, the moon, and RASC in particular. So keep an eye out for that. I'll have Dave Muscle put that up on VicNet so that volunteers can get their names involved in that. And then you can be part of the launch party. And there are the lucky astronauts who will be heading to the moon. I think that's an 8 to 10 day mission. And Frank also indicated that once we have a date for splashdown, there will probably be a splashdown event at Telus World of Science as well. So that's it for tonight. Thank you, everybody, for attending. And we will see you Monday, April 13th.